Am I loud enough? Am I too loud? I get told I'm too loud at some of these talks. So. Hi, my name is Roop Ganguly. I'm a solution architect at BigStream. And I'm going to be talking today about demonstrating the benefits of hyper acceleration. The folks at CAST told me no advertising our products and our company, so this is all going to be about the technology. Maybe a little plug-in at the end. That's about it. So what is this technology aimed at? We're really looking at the end of Moore's Law. So this fellow, Gordon Moore, I believe in Caltech in 1965, came up with this law that said every 2 years we're going to get a doubling of processor power from transistors being packed in tighter and tighter. That law held true. It was a remarkable prediction, but it's starting to become more linear now, coming around 2010. There's a lot of reasons for that. I think the primary one that I've read about is basically the power law. We're not able to dissipate the power from these processors well enough. People are doing all kinds of crazy things to address that. But this is the problem we're facing in terms of getting more computation power. So for this crowd here, this is implications for big data. So all of these applications you see here, machine learning, deep learning, behavioral analytics, so online, bash, what have you, their data needs are growing, and they're growing exponentially, and we're not getting this exponential growth from our processors anymore. So what's happening is these applications are hitting what we're calling a performance wall, and we're seeing this, and what's happening is they're becoming compute bound, which is kind of a remarkable thing for me. I started early 2000s as a parallel processing guy. And what you'd worry about is the communication phase of your parallel processing, right? You got the network slow and using TCP, and now it's pretty remarkable. I've been in data science for about 3 or 4 years now, and it's becoming compute bound, which is pretty interesting. So that's the new bottleneck. So we have faster networking technologies. We're getting into 40 gig. We're getting into 100 gig networks that these machines can be put on. Faster solid-state disk technologies. But as this animation shows, the compute is becoming the stop sign for some of the most powerful or important big data applications. So I like to do this interactively. So what are some of the solutions at a high level to this problem? Right? Name some.
More processors.
More processors.
The Wi-Fi, FPGAs.
You read the white paper, very good. Yeah, so that's on the next slide. Another thing you do is better algorithms. So like deep learning is moving to sort of sparse and binary instead of floating point and dense matrices. So you can put the onus on the scientists to try to make their process.
GPUs are doing that, right?
Who's doing that?
GPUs.
Yeah. Well, so that's the interesting question is what so they're aimed at dense matrix.
Yes.
So as you move to sparse, you're paying a lot for not very much sparse.
But
So that's another.
They also support like the lower precision now as well.
Yeah.
On the
Yeah. And there's a battle between FPGA and GPUs. So these are these are the solutions. This guy stole my thunder. So what the prevailing movement is accelerated. So both microprocessor and cloud vendors have responded by coming out with accelerators. And what that really is hardware-based and really platform-specific optimization, acceleration. So both Microsoft and Amazon are putting FPGAs in their cloud. People have heard of the Google Sensor Processing Unit. What they've done is they've settled on TensorFlow as their deep learning platform, and they made an ASIC-based solution that handles that library. But basically, we're trying to break through that wall using these kind of hardware technologies. There's an issue with that. And the issue is that data scientists, and I used to be one, they want to deal sort of with their platforms in a very domain-specific way. So my analyst at an ad tech company wants to do a Spark processor, Presto, or maybe both. The deep learning guy wants to work with TensorFlow, right? They don't want to know about low-level acceleration. They don't even want to call libraries or put pragmas in their code. That would be their preference. when I put up this slide in front of a TensorFlow guy, who I guess he had started programming in CUDA to try to improve performance of his code. His face went white, and he really felt this pain. And then on the other hand, a lot of these bigger organizations actually have performance teams. These are folks that know a lot about optimizing for this kind of hardware, Verilog programmers, etc. But they don't want to know about the domain-specific stuff. They don't want to learn about the high-frequency trading algorithm to do their optimization. So what we've seen in partnering with our companies is that basically this programming model gap causes a lot of complexity, a lot of lack of productivity, can actually reduce your time to insight. Increase your time to insight. So what we've done is we've come up with a hyper-acceleration layer. And so the key intuition here that we're building on is that each of these big data technologies, if you think about it, at the end of the day, what they produce is what I'm going to call a data flow. And what that is, what I think about is your data and then a set of transformations to that data, right, in stages, along with concurrency information and ordering information. So what can run concurrently, and then what order things have to be, where the shuffles are, where the results have to go. But at the end of the day, the DAG comes out of each of these things. Now they're going to look different in some cases. So Spark, actually we've seen that Spark and Presto, the physical plan look actually pretty similar. And TensorFlow and Spark are going to look fairly different, right? You're doing sort of joins in Spark and matrix multiply in TensorFlow. But the point is that what comes out of there is this data flow. And so seizing on that intuition, we've developed a data flow adaptation layer, which adapts each of these data flows to what I'll call a canonical, in quotes, BigStream data flow, whose stages have been pre-accelerated and optimized for this hardware. Okay? So that's where you get the 30 to 30x acceleration, but the key point is zero code change. So that's the key development. And I've given you a very simple story here. There's actually 5 or 6 patented technologies that make it cross-platform and cross-hardware. And this computation routing is also very interesting in terms of routing the correct stage to the correct type of hardware to a heterogeneous mix based on all kinds of, based on whatever concerns you have. But that's the basic idea, that zero code change to get that acceleration. So when I give this talk, people are like, oh, how does that work? That doesn't really work. We want to see it. So this is just a deeper dive under the hood, and this is specific to Spark. I know the title that Ashish gave had Spark in it, but as you can see, this applies to all the different big data platforms. This slide is specific to Spark, though. So in blue is the architecture for normal Spark, and orange is the acceleration component. So in normal Spark, you have a client application. It gets sent to what's called a Spark master. Now that Spark master is responsible for generating code at runtime to execute the stages. It does all this other stuff like app resource allocation, creates executors or slave nodes, and creates these Spark tasks, which in normal Spark are in Java bytecode, using the JVM. So all that you do for this acceleration technology is we grab what's called the physical plan. I mentioned before data flow. That's what we're referring to as a data flow. We grab that physical plan and using patented compiler technology and the runtime system. The runtime is really just a set of API calls that the compiler has at its behest. So the compiler is able to analyze these individual stages of that physical plan and create accelerated versions of those stages. What you want to think about is accelerated versions of these Spark tasks. And it understands the hardware mix that it has underneath it. So, for example, our latest product, which is up on Amazon right now, is a software base. So we compile accelerated in native C++ using a lot of different optimizations. But it applies to GPUs and FPGAs, whatever hardware you have under. So the key here is that we have a one-time cost of adapting the Spark data flow to our data flow, and then it's accelerated. And so the key takeaway from this slide is the real estate, which is, we're over here on the right side. We can't possibly touch the application. That's where the zero code change comes from. So any questions about this architecture?
And when you ship the data back?
It's all in tungsten under the hood, which is the optimized data format for Spark. So we do all our, so when we hand it back to Spark, it's tungsten, it's exactly what it expects.
What's the Gorilla plus plus? I like to know.
My CEO can answer where he got the name from.
Is this C++ piece generator?
Yeah, that's a C++, yeah.
It's a DSL for FPGA.
Ah, okay. Fair enough.
It's like a C-like language, and you write that, and we have to change to synthesize it all the way to FPGA.
Okay, so you don't have to deal with basic C++. It will generate that for you. Okay, which is nice. That's the reason why it's the Gorilla, right?
So what is exactly it's doing? Is it creating better bytecodes, or it is?
No, so it's not creating bytecode. So
It
it looks, what we have is compilation for each of the different stages. So you have the stages, which are like a broadcast join or a filter. We have a compiler that knows how to compile that in native C++. So it's not bytecode anymore.
Okay.
So they're a parallel set of tabs. And the one thing I didn't mention is the only other change we really make to the Spark architecture is we put a 1-0 check in the executors, the slave node, the slave processes, to check to see if there's an accelerated version of the tab. For whatever reason, if we can't accelerate a stage, it will default to Spark behavior.
Also, some part of my task will run on your optimized.
Hopefully all of it.
Okay.
But if something happens,
Okay, then it'll fall.
99% case that we can't accelerate, it defaults to Spark. And in either case that this gentleman mentioned, we hand back to Spark the data format that it expects. Okay, so I'm going to show a couple of use cases how this stuff works. So the first one is the simplest one. It's just a business intelligence query. It's based on, people are familiar with TPC, DS benchmarks, are just a set of queries that folks use to show that their decision support system is better than somebody else's decision support system. It's just a Spark SQL query. This is a fragment of it. So some analyst is interested in when stuff was sold in this table. And so this is just a query that people are using as a benchmark. The input is approximately 2 gigabytes of data. It's in Avro. I know people, data scientists here, are like, where are the terabytes of data? Well, you don't want this talk to take an hour and a half, right? So that's why 2 gigabytes of data. But it does demonstrate the acceleration of the stages, and you'll see the speed up. So what we do is we just simply simultaneously run the software accelerated. This is the one that's compiled in C++, and the unaccelerated on identical Amazon EMR clusters. So we provision them in exactly the same way. And that's shown here. People can see, this is, for people that are familiar with Amazon, this is just your cluster list. We have 2 clone clusters here that we're going to run this stuff on identically. So let's start the video. Okay, so I'm just highlighting the demo and a demo clone. I forget which one was accelerated. We'll see now. So on the left side is unaccelerated, on the right side is accelerated. And what you'll notice when what's highlighted there is just configuration flag. Spark, BigStream.accelerate is equal to false. Sorry if you can't see it all, I'll try to read it out. And so we have cut and pasted the command to the other cluster. So it is exactly the same code. It's TPCS Q7 compiled in exactly the same way. The only thing we're doing over here is we're going to change the accelerate to true. And now, let's race. We gave them a head start, actually. So this is just normal Spark initiation. It's, like I'm saying, it's creating the physical plan, it's creating that DAG. I don't think this video shows, so there's an extra compilation step on the right side, right, which takes several seconds, where we look at the stages, analyze them, and we're able to generate the C++ code. So now it's starting to execute the individual tasks on the executors, and we've finished on the right side. This guy's still churning. So this is meant to be annoying because we're waiting for normal Spark to finish.
Yeah. Is this Spark 2.0?
So it's 2.0.
2.0.
Yes. So now they've finished, and now we're going to do a quick speed up calculation. So the benchmarks print in milliseconds, the amount of time, so this guy took 125 seconds. Accelerated that mouse wheel back. So it's about a 3x speed up, and this is with the software acceleration. Right? So for no code changes, 3x speed up. So we're pretty excited about that. And I'll show you later, if you guys really want to try this out, you should. It's available on Amazon right now as we speak. So one more use case I want to show you is an ETL ad tech use case. So for those people that have worked in data science, especially in digital media, this is pretty familiar. I've heard people talk about Kafka all day, so I won't go into detail about that. But basically, there's a bunch of users out there creating a bunch of ad tech data coming from the real world, going into the analytics world. It gets staged on a Kafka server, which basically creates topics, sequentializes it, and you're able to subscribe to that. And so we have a Spark streaming application that's consuming data from that Kafka server. This is very familiar. And then probably down the line, it sends the results of its queries out to some machine learning. So what we're gonna show you here is the results of accelerating this, the Spark streaming consumption from the Kafka server. So what you're looking at here is identical pieces of code, top and bottom. Sorry, again, this is hard to read, but this is just some query data frame. Country is not null, auction ID, aggregate by price. So some analyst is interested in the result of this query, or some machine learning wants to make that into a feature set down the line. So what we're going to do is we're going to dynamically compile this code for an FPGA-based acceleration up here. This is going to run on normal Spark with a fairly powerful processor, a late generation Intel Xeon. And so let's compare. So you'll notice the only edit change we make over here, again, is this flag, spark.bigstream.accelerate, that's set to true in our definite interpreter. And that's it. Now we have accelerated Spark running up here on the FPGA. We'll start again, give them a head start. I don't know why we can do that. So on the left side, is the code. On the right side, what you're going to see in these speedometers is the rate of consumption of data. And that's really the game changer here, right? The faster per unit time you consume the data from Kafka, whatever, the better analytic you can run, the better answer you can get, the faster answer you can get. So those rates are coming across right now. I'll read this for you guys. This is about 74 megabytes per second, and up here we're getting around 6x, 626 megabytes per second. And that's actually with a previous generation FPGA. This is shot a couple months ago. And the other thing we notice is the scheduling delay for the accelerated is going to 0 because we're meeting the deadlines for consumption of the data. So every time a piece of data comes in, it has a deadline for consumption based on the configuration of the Kafka server. And so we're able to make that delay 0 here, whereas here, it's sort of growing without bound. So this is a really bad situation, right? Spark here is not able to execute the analytics fast enough to keep up with this deadline for consumption from Kafka. And so that's, I mean, there's going to be decimation or dropping of data. So really what, this is actually an interesting use case where we've actually solved the problem that someone might have had with their Kafka configuration, because no one's going to tell the producer to stop producing data. So we won't wait for that to finish. Okay, so that's the demonstration of hyperacceleration, and like I said, this is our shameless plug here. We're available on Amazon Web Services. It takes about 5 minutes to sign up, and then you're whitelisted to use BigStream acceleration. And if you have your Spark SQL applications, you can get this kind of acceleration. And just last thing to show you just how easy it is. So once you sign up, you're whitelisted for this. So that is a bootstrap. So folks that are familiar with Amazon, one of the steps is specifying potential bootstrap options in creating your cluster. So all you got to do is specify that as a bootstrap, and your cluster comes up with acceleration. Actually, as default, so you don't have to even set the flag to get the acceleration. You can set the flag to turn off the acceleration, but why would you want to do that? So that's it.
So it is up to you to get the proper instance types, like with FPGAs or the GPUs, in order to leverage the
Yeah, so right now, there's, FPGAs aren't available right now on
They're
Amazon.
coming, right?
On Amazon.
They're coming.
They're
They
coming.
announced them in the last conference. They announced them.
Yeah, they're announced. And we actually have an early agreement with them to work on it.
But the GPUs are available.
I don't know. GPUs available?
The old generation is still available. The new one is coming up. I'm not sure if I haven't checked the release time, but both of them will be available. So the latest GPUs and the FPGAs.
So this works right now just with the CPU at this point.
Oh, okay, so it's only software.
Yeah, it's only software at this point. But that's coming soon.
Because I don't see any options. So,
No.
you know, GPU.
Well, you can select whatever instance you want of CPU. Yeah. But that's. Thanks. That's all I had. Any questions?
Does it work better with IO bound, CPU bound workload? Or
So that's an interesting question. So typically you would think it would be compute bound applications, but we also accelerate things like the Kafka connector and JSON deserialization and things like that. Those are also accelerated stages. So it's going to accelerate all that stuff. It can make bits fly over the wire any faster, but the consumption of the data by TCP or Kafka is accelerated.
So map job will run faster than shuffle. Shuffle will have to get.
They'll both get acceleration to different degrees, I would say.
Is it only available on AWS or you can?
It's coming on Azure in the next couple of weeks.
If you have your own in-house private clouds, can you use
So we do on-premise also. We work with people. We're doing POCs right now on-premise. So if you're interested, please talk to us.
I was wondering, how do you generate the FPGA code? Because that's the tough part. Gorilla
That's
Plus
a bit of the secret sauce.
Yeah, kind of like the I know that's the whole point, right?
So basically, what you want to think about is we have pre-existing bit files that are parameterized, that can be configured for each of the different types of stages that you have. And those can be, in milliseconds, can be loaded onto the FPGA at runtime in the exact same way.
So you don't generate the VHDL
No.
code and then...
That's already been.
Okay, fair enough. And the last question is, with the Spark 2.0, with the Tungsten project, they actually kind of unroll the loops or unroll a lot of objects into simple code that actually to leverage the SIMD instruction in the CPU. So are you getting that code that is generated from the Tungsten?
Yep.
Okay.
This
acceleration
is on top of
Okay, so you take that code and you compile it to C++.
Correct.
Okay, so you don't generate your own code because
Nope.
Tungsten tool already is doing that.
Yep.
Okay, fair enough.
We run on those.